friends. I am Satish Lele. I am a chemical engineer. I am working in field of piping for last 30 years. This video is part of my chemical process piping channel on YouTube. This video is about protection of pipelines from corrosion. Protection from corrosion, surface treatments. These can be applied coatings, reactive coatings, sanitization, biofilm coatings, coating protection, sacrificial anode protection, phenolic protection. Applied coatings, plating, painting, and the application of enamel are the most common anti-corrosion treatments. They work by providing a barrier of corrosion-resistant material between the damaging environment and the structural material. Aside from cosmetic and manufacturing issues, there are trade-offs in mechanical flexibility versus resistance to abrasion and high temperature. Platings usually fail only in small sections, and if the plating is more noble than the substrate, for example, chromium on steel, a galvanic couple will cause any exposed area to corrode much more rapidly than an unplated surface would. For this reason, it is often wise to plate with active metal such as zinc or cadmium. Painting either by roller or brush is more desirable for tight spaces. Spray would be better for larger coating areas such as field depths and waterfront applications. Flexible polyurethane coatings can provide an anti-corrosive seal with a highly durable slip-resistant membrane. Painted coatings are relatively easy to apply and have fast drying times, although temperature and humidity may cause dry times to vary. Reactive coatings. If the environment is controlled, especially in recirculating systems, corrosion inhibitors can often be added to it. These form an electrically insulating or chemically impermeable coating on exposed metal surfaces to suppress electrochemical reactions. Such methods obviously make the system less sensitive to scratches or defects in the coating, since extra inhibitors can be made available wherever metal becomes exposed. Chemicals that inhibit corrosion include some of the salts in hard water and water systems are famous for their mineral deposits: chromates, phosphates, polyaniline, other conducting polymers, and a wide range of specially designed chemicals that resemble surfactants, which are long-chain organic molecules with ionic end groups. Sanitization. Aluminium alloys often undergo a surface treatment. The electrochemical conditions in the bath are carefully adjusted so that uniform pores several nanometer wide appear in the metal's oxide film. These pores allow the oxide to grow much thicker than passivating conditions would allow. At the end of the treatment, the pores are allowed to seal, forming a harder than usual surface layer. If this coating is scratched, normal passivation processes take over to protect the damaged area. Sanitizing is very resilient to weathering and corrosion, so it is commonly used for building facades and other areas that the surface will come into regular contact with the elements. Whilst being resilient, it must be cleaned frequently. If left without cleaning, panel edge staining will naturally occur. Biofilm coatings. A new form of protection has been developed by applying certain species of bacterial films to the surface of metals with highly corrosive environments. This process increases the corrosion resistance substantially. Alternatively, antimicrobial-producing biofilms can be used to inhibit mild steel corrosion from sulfate-reducing bacteria. Coating protection. Coating protection, or CP, is a technique used to control the corrosion of a metal surface by making it the cathode of an electrochemical cell. The simplest method to apply CP is by connecting the metal to be protected with a piece of another more easily corroded sacrificial metal to act as the anode of the electrochemical cell. The sacrificial metal then corrodes instead of the protected metal. For structures where passive galvanic CP is not adequate, for example in long pipelines, an external DC electrical power source is sometimes used to provide current. Cathodic protection systems are used to protect a wide range of metallic structures in various environments. Common applications are steel water or fuel pipelines and storage tanks such as home water heaters, steel pier piles, ship and boat hulls, offshore oil platforms and onshore oil well casings. Metal reinforcement bars in concrete buildings and structures. Another common application is in galvanized steel, in which a sacrificial coating of zinc on steel parts protects them from rust. Cathodic protection can, in some cases, prevent stress corrosion cracking. Sacrificial anode protection. For effective CP, the potential of the steel surface is polarized or pushed more negative until the metal surface has a uniform potential. With a uniform potential, the driving force for the corrosion reaction is halted. For galvanic CP systems, the anode material corrodes under the influence of the steel, and eventually it must be replaced. The polarization is caused by the current flow from the anode to the cathode, driven by the difference in electrochemical potential between the anode and the cathode. Anodic protection. Anodic protection impresses anodic current on the structure to be protected. It is opposite to the cathodic protection. It is appropriate for metals that exhibit passivity. For example, stainless steel and suitably small passive current over a wide range of potentials. It is used in aggressive environments, such as solutions of sulfuric acid. Pipelines are routinely protected by a coating supplemented with cathodic protection. System for a pipeline would consist of a DC power source, which is often an AC-powered rectifier and an anode, or array of anodes buried in the ground called the anode ground bead. The DC power source would typically have a DC output of between 10 and 50 amperes and 50 volts, but this depends on several factors, such as the size of the pipeline. The positive DC output terminal would be connected via cable to the anode array, while another cable would connect the negative terminal of the rectifier to the pipeline, preferably through junction boxes to allow measurements to be taken. Anodes can be installed in a vertical hole and backfilled with conductive coke material that improves the performance and life of the anodes for laid in a prepared trench, surrounded by conductive coke and backfilled. The choice of grounded type and size depends on the application, location and soil resistivity. The output of the DC source would then be adjusted to the optimum level after conducting various tests, including measurements of electrochemical potential. It is sometimes more economically viable to protect the pipeline using galvanic anodes. This is often the case on smaller diameter pipelines of limited length. Galvanizing generally refers to hot dip galvanizing, which is a way of coating steel with a layer of metallic zinc. Galvanized coatings are quite durable in most environments because they combine the barrier properties of a coating with some of the benefits of cathodic protection. If the zinc coating is scratched or otherwise locally damaged and steel is exposed, the surrounding areas of zinc coating form a galvanic cell with the exposed steel and protect it from corrosion. This is a form of localized cathodic protection. The zinc acts as a sacrificial anode. Galvanizing, while using the electrochemical principle of cathodic protection, is not actually cathodic protection. CP requires the anode to be separate from the metal surface to be protected, with an ionic connection through the electrolyte and an electron connection through a connecting cable. volt or similar. This means that any area of the protected structure within the electrolyte can be protected, whereas in the case of galvanizing, only areas very close to the zinc are protected. Hence, a larger area of bare steel would only be protected around the edges. Rate of corrosion, a simple test for measuring corrosion, is the weight loss method. The method involves exposing the clean weighed piece of the metal or alloy to the corrosive environment for a specified time, followed by cleaning to remove corrosion products and weighing the piece to determine the loss of weight. The rate of corrosion R is calculated as R equals kilowatts divided by density, area and time, where K is a constant. W is the weight loss of the metal in time T, that is the surface area of the metal exposed, and M is the density of the metal in grams per cubic centimeter. Corrosion in nonmetals. Most ceramic materials are almost entirely immune to corrosion. The strong chemical bonds that hold them together leave very little free chemical energy in the structure. They can be thought of as already corroded. When corrosion does occur, it is almost always a simple dissolution of the material or chemical reaction, rather than an electrochemical process. The common example of corrosion protection in ceramics is the lime added to soda-lime glass to reduce its solubility in water. Though lime glass is not nearly as soluble as pure sodium silicate, normal glass forms submicroscopic flaws when exposed to moisture. Due to its brittleness, such flaws cause a dramatic reduction in the strength of a glass object during its first few hours at room temperature. Corrosion of glasses. Glass disease is the corrosion of silicate glasses in aqueous solutions. It is governed by two mechanisms: diffusion controlled leaching by an exchange and hydrolytic dissolution of the glass network. Corrosion of polymers. Polymer degradation involves several complex and often poorly understood physicochemical processes. These are strikingly different from the other processes discussed here, and so the term corrosion is only applied to them in a loose sense of the word. Because of their large molecular weight, very little entropy can be gained by mixing a given mass of polymer with another substance, making them generally quite difficult to dissolve. While dissolution is a problem in some polymer applications, it is relatively simple to design against. The more common and related problem is swelling, where small molecules infiltrate the structure, reducing strength and stiffness and causing the volume change. Conversely, many polymers, notably flexible vinyl, are intentionally swelled with plasticizers, which can be leached out of the structure, causing brittleness or other undesirable changes. The most common form of degradation, however, is a decrease in polymer chain length. Additives can slow these processes very effectively, and can be as simple as a UV-absorbing pigment, like titanium dioxide or carbon black. Mechanisms which break polymer chains are familiar to biologists because of their effect on DNA. Ionizing radiation, most commonly ultraviolet light free radicals, and oxidizers such as oxygen, ozone, and chlorine. Ozone cracking is a well-known problem affecting natural rubber, for example,